Okay. Um, so if you had one of my undergrad classes when I first teach programming, and this is actually, I think I mentioned this last class, but Dr. Locklear has this idea called the grand ideas of computer science. And that's why when you take different classes in computer science, a lot of times you'll hear the same topics, but from different angles or through different lenses, because they're all very intertwined. So when I first teach, beginning programming to, a freshman or sophomore or whenever they first take that class, we talk about, there's three kinds of programming languages and there's two kinds of programming languages because we're kind of looking at languages from different angles. So one of the slides I have in there typically is this idea that there's three kinds of programming languages. We have machine language, we have low-level languages, and we have high-level languages. All right. So machine language. And here, just real quick, let's go to 1.34 in the book. I just want to see if they're talking about anything interesting in there that I want to toss in here before I just dive into my 1.34. Is that what it said? Okay, yeah, nothing special. The way I talk about it, I think is probably better than that. All right, so at the end of the day, machine language is zeros and ones, right? That's what computers like. We've already been talking about that, but that kind of solidifies it. We haven't been converting things in binary base 2 for our health. That's not a friendly format for people, right? We even saw with our little converter program thing we wrote that, not that scary of a value in decimal turns into a lot of ones and zeros that we don't like. But computers do. And as we keep going through this stuff, we're going to start seeing why. At the end of the day, for right now, we want to just accept the idea that computers like ones and zeros because they're digital, on or off. That's how they can represent a bit of information. And then lots of bits of information can be used in conjunctions to represent larger pieces of information. And then we have to think about how do those guys work together and stuff like that. But the point of this is that for a human being, we aren't going to be typing stuff in machine language. All right. Now we can go through, I think the book has you do it. We can go through a little exercise of, okay, here's your low-level language instruction. We'll talk about that in a few minutes. And go ahead and convert this into what the machine language version of it would be. We can do it for a couple of lines, right? Just as an exercise for the reader. Like, okay, that's actually instruction 010001, and you can make it work. But this is not the type thing that you want to sit around 8 hours a day tapping out zeros and ones with a 2-button keyboard. That's not us. We can't handle that. All right. So the next thing here is this idea of a low-level language, and this has a one-to-one relationship with the CPU. And I think we did talk about CPUs, right? Did I talk about like the magic trick stuff? Okay. Yeah. So this has a one-to-one relationship with the CPU, which effectively says every line of code we write in a low-level language is relative to exactly one magic trick on the CPU. And the idea for our CPUs is that each of those magic tricks does a little tiny thing. Okay, I think we had to do the little, had your hands moving your hands like this. Nobody's impressed if you can do this, but you do enough of those things together, you solve a real problem. So a low-level language, we would be giving the CPU step by step by step instructions, very granular things. We would tell it to wiggle the thumb or move the finger. None of that's all that impressive, but at least it looks more English-like. It's not zeros and ones, so it's more in our wheelhouse. Okay, still not what we maybe want to spend all day, every day doing, but we could. Make sense? And we'll look at some low-level stuff here in a few minutes. Actually, let's look at it right now. Good point here. Did I show you Hello World in assembly before? Okay. This is the one I usually like using. Currently offline. All right, we're not using that one. All right, that's good enough. Okay. So this is an assembly language program. It actually is using Linux as the core operating system. So what we're actually looking at here is a low-level language that happens to use a power tool. A couple of power tools, and I'll explain that in a few minutes. Okay, forget about this junk up here. That's just kind of required stuff. Now, down here at the bottom, we have our data section. So we have a couple of variables we're creating in here. So we're establishing some memory and putting some stuff in that memory. What are we creating? Well, we're creating a string called hello world. Don't worry too much about how that's actually happening. And then this other guy, so this guy's called the message, MSG. The message is a data byte, which is the pointer to the front of hello world. And then we have len, which is going to be the length of that message. Okay? It's two pieces of information we're holding on to. The message itself and how long the message is. And we'll talk about why we need to know how long a message is here in a few minutes. Unrelated to this, we're actually going to talk about it through C and then swing back through into this stuff. So now this is really our instructions. This is the heart of the program. Okay, those are the magic tricks. So this is a magic trick, this is a magic trick, this is a magic trick. Each one of these lines is one magic trick on the CPU. Make sense? All right, so we want to go through and see what's happening here. And really, this is a program that is written to interface with the core operating system of Linux. So this guy is actually being set up to talk to the Linux kernel. So this really is showing us kind of a behind-the-scenes look at how operating systems make the lives of a programmer easier. Because what we're looking at here is actually a pretty simple assembly language program. If we didn't have this, complex underlying operating system like Linux and we had to write all the pieces here ourselves, we would not be happy. Okay, this would be a lot scarier, and I'll point out the piece that would explode into possibly thousands of lines. All right? So this first instruction is called move. I'm moving some element into some place in memory. Okay, we talked about some different memory types, and we mentioned registers, I think last time. We said registers are really, 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 really fast memory. This dude's a register. So we're saying we're going to put the length of our message into this storage location. We don't know why, just for right now, we're putting it there. I'm going to take that length, I'm going to put it in this storage location. I'm going to take the message itself, I'm going to put it in this storage location. Then I'm going to take the number 1. Go ahead.
Is it creating ECX or?
No, these are known pieces of memory. These are known registers.
Oh, those are, even though LEN, that's.
LEN we created down here.
Oh, you created.
Yeah, here's LEN,
Okay.
and here's the message. So those are 2 variables.
Gotcha.
Then these are actually pieces of hardware. This is the name of a little memory place. This is another name of a little memory place.
Okay.
All right. So we're going to load this piece of information into this memory place. We're going to load this piece of information into this memory place. Then we're just randomly going to put the number 1 in this memory place. And we have to know what the 1 stands for. Most operating systems, most modern operating systems, this is really something that comes from something called a POSIX compliant operating systems, which isn't something we're going to talk about in here. It's more of an operating systems concept. But POSIX compliant operating systems, one of their things they talk about is we have these standard streams, I/O streams. And typically POSIX says there's 3. We have something called standard output. We have something called standard input. We have something called standard error. All right? So, and what becomes interesting about this, and this really comes down to the whole POSIX standard, standard input is the keyboard. That's reading stuff in from the user. Okay? Now, standard output goes to the screen. Standard error also goes to the screen. So why do I need 2 different streams that both go to the screen? Well, they're both going to the screen. What, can I just use one of them? What do we sometimes want to do with error messages? Well, what's a log file? If I say something like a log file, what am I talking about?
It gives you all the data.
Yeah, so kind of a history of stuff that's happened. Now, what would be more helpful, for us to log everything that's ever gone onto our screen or for us to log error messages? It might be helpful to just see error messages, right? Things that have gone wrong. So if we split that into 2 separate streams, we could have normal output go to the monitor. And then by default, normal error output goes to the monitor, but we can then redirect the error and say go to log files. So only the error messages, assuming the programmers chose to write the error messages over system, like for instance in Java. You can do system.out.println and it prints something to the screen. You can also say system.err.println and it prints it to the screen, but it's actually through a different channel. And if you do that on a lot of terminals, it'll show up in red. System.err.println will show up in red because it's actually the error, standard error. All right. Unimportant in the big scheme of things, it's more just extra knowledge or whatever. But we are moving the number 1 in here because the number 1 happens to relate to, in the Linux operating system, the value for standard output. So we must have 0, 1, and 2 for the 3 output streams or the 3 streams. So 0 is probably standard in, 1 is standard out, 2 is standard error. All right. So we're just going to load a 1 into EBX. Then we're going to load just haphazardly a 4 into EAX. And it just so happens that when I say something, I know we maybe have written this before, but what's an API? We talked about APIs? Probably heard of them before. What is an API? Okay, so application programming interface, or sometimes it's abstract programming interface. Call them interchangeable. What is it though?
It's like a library. You can directly call and it will abstract as all the details.
Okay, so this is, and we kind of operate off of the word you gave it. So it's an interface between an application, for example, Linux, and third-party applications. Maybe our program. All right, so the Linux operating system, like many other pieces of software, provides an API. They have a whole bunch, and usually these guys are referred to as system calls. Okay, but at the end of the day, it's an API. Here's a whole bunch of different ways that you can directly talk to the Linux operating system from your program to get Linux to do things on your behalf. That makes sense? So one of these system calls in Linux is called syswrite. Say this again. Well, I guess sort of, given that they are talking to the operating system itself to get stuff spit out to the screen. But then they're also talking to called the Java virtual machine, which has an API to tell the virtual machine to run the program and stuff like that. So Eclipse itself would be more like the user program, the program we write, and then it would interface with the APIs of Java as well as the underlying operating system. Now, having said that, Eclipse itself also provides an API because it supports plugins. So if somebody wants to add something to Eclipse, some functionality, they can write a plugin for Eclipse in terms of the things that Eclipse lets you manage. Make sense? Yeah, so I mean, APIs are everywhere. We see them, if you want to write a mobile application that accepts payments with PayPal or can make payments with PayPal, you're going to hook into PayPal's API. So that you can do PayPal-y stuff without inventing PayPal. There's already this guy out there that knows how to do PayPal stuff because his name is PayPal. And we're going to just leverage his things. We just need some tools that allow us to say, hey, I need to make this amount of money to this guy. Go. And then it does the payments.
Is it kind of like, say, Arduino, Arduino?
Yeah.
Okay, it's like referencing libraries, like pulling in different libraries. Same sort of thing.
Same sort of thing. All right, so one of the many system calls in Linux is called syswrite. Okay, and this magical program that's in the Linux operating system knows how to write something to the screen. Now, it seems so boring to us, but under the hood, writing something to the screen is quite complex. Because what is required to write something to the screen? If we draw that picture, so now we have to start thinking about the actual architecture of our whole computer system. So at the end of the day, we want the stuff to show up on the monitor. All right. Now what's the monitor hooked into?
Motherboard.
Okay. So at the high level, we'd say, well, it's hooked into the computer. Okay, but it's hooked into a, it's not plugged directly into the CPU. Monitor is plugged into graphics card. All right, so that's plugged into the GPU. The GPU, you push it down into the motherboard through like PCI Express or something like that. So there's some different interfaces with the motherboard that allows you to have external cards like graphics cards hooked into it. So the GPU is going to be hooked into a bus on MB. So one of the buses on the motherboard, depending on the age of the graphics card. Any new graphics card will be PCI Express, but older it would have been PCI or ISA slots before that. Probably, have any of you ever seen an ISA slot? Just walk around the department and look at some of the old boards on the wall. Those are ISA slots. PCI are the shorter white ones. You've probably seen them. And then PCI Express is significantly faster. But anyway you cut it, these are interfaces to allow you to plug in devices that ultimately hook into one of the buses within the motherboard. Because that's what, I mean, what's a motherboard? A motherboard is just a whole bunch of communication channels that allows this to talk to this, usually with various speeds. All right, some things need more speed, some things need less speed. All right, so we have the monitor here, which is going to talk to the GPU, which is hooked into some bus on our motherboard, depending on what the technology is. Okay, now that bus, somebody has to talk to that graphics card, who then is going to tell things to spit out to the monitor. Right now, the graphics card itself, is this guy a power tool? Is there a bunch of stuff in our modern graphics cards that know how to write stuff out to monitors? So is this guy right here doing a lot of work that historically maybe the computer had to do itself? Today we think of the graphics card as being kind of the separate unit, right? So it's built as almost a standalone thing. It's still part of the equation. It's still one of the communication channels. The CPU sends some stuff out and blah, blah, blah. It ultimately is a matter of asking the GPU to interact with the monitor. Okay, and then it's going to feed it the data that it needs to interact with. Maybe the GPU is doing some of that heavy lifting. But if we go older and we think about something like a VGA compatible, graphics processor or something like that, we're talking bare bones. We don't have these powerful third-party libraries like OpenGL or DirectX for, doing powerful things to the screen. Things that we think about today, like getting 3D graphics and stuff like that on the screen. So we're just talking about putting some text, having some pixels light up on that screen. So this monitor is a piece of equipment which is talking directly to this guy, and there's an interface in this monitor where this graphics card is going to have to spit stuff in over that VGA or the DVI or the HDMI interface for this monitor, and it's going to have to give it the correct signals to make certain things light up in certain places on that monitor, right? So that means the GPU is going to have to feed this guy the right kind of signals to make things light up. Well, who's going to feed the GPU the information it needs? Well, probably the CPU. All right, and who feeds the CPU the instructions? System RAM. Okay, and where does RAM get its instructions? From the hard drive. Now, what ultimately allows the hard drive to load stuff into RAM, which then feeds into the CPU, which then travels over the bus, ultimately talking to the GPU, going out to the monitor? Who's responsible for actually telling? Because these are all individual devices, right? I mean, that's what these are. They're individual devices. These just happen to be a whole bunch of little machines that live in, near proximity to each other. Now, the mechanism by which a RAM delivers stuff to the CPU is our process. We kind of drew a picture of that before. So out of RAM, we form processes. Whatever, like that. But somebody has to be in charge of looking up on the hard drive, loading something into RAM, generating some processes, scheduling and feeding them to the CPU, ultimately transmitting data. So this is typically an interrupt. So you typically have something like an I/O interrupt. It's called I/O interrupt. So the CPU gets paused, so some information can travel over one of the buses to the GPU, ultimately to spit something out on the monitor. This is just to get stuff on the monitor. What if we were writing out to a USB hard drive, or we were talking to our Ethernet card or our Wi-Fi card? We're just adding more pieces of equipment to this picture, right? So we're keeping this super simple. This is like a really mundane computer we have here that doesn't do much. This is an old school computer that just hooks to your monitor and has stuff that shows up on the screen. But ultimately, who's in charge of making sure all these individual pieces all communicate with each other in the right way? Yeah, the OS. So in our example right here, we're using Linux in the current example we're looking at. All right, so the Linux operating system knows how to make all these guys talk to each other. All right, so it's a computer program. That's actually a whole bunch of computer programs all running at the same, running together to make your computer work, to make it easier for the human being to interface with this stuff. Because none of us, so we're going to put us in here. Here, we'll put a little smiley face. Okay, that's us. All right. So the user, if we didn't have this operating system, we would have to talk to the hard drive directly, or talk to RAM directly, talk to the CPU directly. So the processes here, this is actually kind of part of what the operating system does. So I'll just truth in advertising, I guess, here. We have to talk to the CPU directly, or communicate over the bus directly, or talk to the graphics card directly, or talk to the monitor directly. That's not for us, right? We're not going in there with the soldering iron and touching two wires together to make something occur, right? We sit there with the keyboard and the mouse, and we're watching Netflix. We're not operating at that level with the computers today. But that stuff's still in there, right? If I break apart this computer, are we going to find some techie looking stuff in there that I'm going to wish I hadn't just broken? All right, so this operating system here acts as an intermediary between us and all this hardware. So I mentioned a few minutes ago that this little program we're looking at here, this little hello world program that's going to spit hello world out to the screen, is actually a power tool. This dude here, notice I've made him fairly large. He does a lot to make our lives easier. Even though we're looking at a program like this and we're like, oh, this doesn't look like something I want to do. All right, so one of the many things that this dude knows how to do is this system call called syswrite. And the syswrite system call ultimately knows how to do the magic of getting something going through all of this crap, ultimately showing up on the monitor. Okay? At the very least, we can sit here and say that we're thankful that it's doing that for us, right? We perceive that at the very least, it would be a lot of work, a lot more work, if we had to do that ourselves. Okay? So the operating system is doing us a solid. All right, whether it's Linux or whether it's Windows, whether it's Mac OS, which is actually a Unix-based OS, they all have an API. They all have system calls. They might be named a little bit different, but they basically do the same thing. Windows is going to have a system call for writing crap to the screen, right? And it might just work just a little bit different. And I'll talk about that here in a second, because if we really think about what's happened so far, These first 4 lines, I've just staged information. I haven't actually done anything real. And I really even haven't had a whole lot of like logic behind it. I had 4 pieces of information here. I had a string. I had the length of the string. I had the number 1 for some reason. And I had the number 4 for some reason. Okay, what did I do? I ran around. I hid them in different places. That's all I've done. The first 4 lines, I just put crap in some buckets. What if I stopped right there? Okay, that's called cleaning your room. I put stuff away. It might not have been in the good spots. Okay. Now, then, I interrupt the CPU. Specifically, this little dude right here is saying, call the Linux kernel. Call that guy. All right? And when we call the Linux kernel has a go-to move. The very first thing he does when the CPU interrupts him and executes the kernel is he looks in that register right there. He looks in EAX. He says, okay, CPU just called me up. CPU just banged on my door. Says, kernel, it's your turn. So kernel's going to go look in EAX. Oh, number 4. Of course, it had to be number 4. Okay. Number 4 is syswrite. So then the kernel says, okay, well, what do I need? I'm going to need to know where he wants me to write this to. I'm going to need to know what he wants me to write. And I need to know how long it is. That way I make sure I stop at the right point. I don't keep writing whatever's in memory after that in perpetuity. So the next place he's going to look is going to say, oh, well, I expect if this programmer knew what they were doing. I expect that he would have told me where he wants me to write the information in EBX. So the next thing he's going to go look in EBX and say, he wants me to write it to 1. Well, what does 1 correspond to? It corresponds to standard output. Okay, great. So now as the Linux kernel here, I know that I'm writing something and I'm writing it to standard output. Then it's going to say, okay, well, what does he want me to write? Well, assuming he knew what he was doing, he would have put his message in ECX. It had to go into that bucket. So now I'm going to go look in ECX and say, okay, here's my message. I got this hello world, and who knows how long this guy goes on for, but I effectively have a pointer to the beginning of this string. So this is a memory location. Okay? So it's okay. So now I know where his message begins in memory. Okay, it begins here, and okay, the last thing I need to know is how long is his message. That way, as I start dancing through memory 1 byte at a time, I know when to stop. So I'm not, printing crap out that's part of the operating system or part of your tic-tac-toe program or whatever it is. I need to know how many bytes. All right? So, and Linux is going to say, you know what? If this programmer knows what he's doing, he would have told me how long it is, and he would have put that in EDX. So now the kernel has retrieved the 4 pieces of information it needs. The first piece of information is, what am I doing? Which then set it up for saying, since I'm doing a syswrite, I need 3 more pieces of information. And he goes and finds those 3 pieces of information in the very specific places. And then he ultimately does the crazy magic trick of printing hello world through all this junk and ultimately having it appear on the monitor. That's a power tool. Right? All we had to do is throw things into 4 buckets. Yeah.
How many, is it E, just A through D?
It depends on the architecture we're dealing with. In the book here, we're going to start looking at what's called an ARM architecture, which is as opposed to Intel-based architecture, which is what we're looking at here. If you go back to old 8086, old processors, you only had a handful of registers. As you get newer processors, you get more registers, and they become larger in size. So you have all the old ones. So AX and BX, for example, from the 8086 were 16-bit registers that had a high and a low. So you had 8 bits high, 8 bits low if you only wanted to use a byte. But then you have, EAX, I think, are 32-bit registers. Then you have some 64-bit registers and some of the newer chips. So it just depends on the architecture. Whatever chip you're working with, there will be an architecture list that says, here are all your memory locations that you have to work with.
Okay.
And then there's some special ones that are kind of, memory is memory, let's say, but certain registers are only used for certain things. Like you have things called like flags and stuff like that. So sometimes you might say, well, this bucket's just as good as this one, but like this one's like is important.
Yeah.
You don't want to use this one because something else might put something in there that you need. And whatever you put in there might get overwritten. So that's kind of just more of the architecture.
Okay.
But don't, I guess I would say don't really overthink it. Think of it kind of like getting a new car, where you kind of learn where all the cup holders are and stuff like that. And you know most cars have some cup holders. Most cars have, you know, this, that, and the next thing. But different cars might have a little different configuration or might have more or less cup holders. So once you learn that architecture, you can write assembly code for it. But the reality is for most humans, we're not going to write assembly. You know, we're going to write a high-level program and have, you know, some other servant of ours turn it into assembly. Okay? Except in here, which we'll write assembly. And that's mostly because I don't like Edwin. That's E-D. All right. So in any case, we staged 4 pieces of information, then told the Linux kernel to take it over from there. Linux kernel goes and does its thing, gets hello world spit out to the screen magically, because this guy was a heavy hitter. Then we come back to the program. Forget about this line for a second. Right? Just pretend like it's not there, because it's really unimportant. It's for when you write something back out to Linux, but I'm just going to ignore it for a second. Up here, we moved into EAX, a 4, right? Because that told the kernel, when we actually told the kernel to take over, that we wanted to do a syswrite. We're done with our program now, so we want our program to exit. So we overwrote EAX now with a 1. We changed that 4 to a 1. We didn't change any of this other stuff. We just left it. Who cares? This program's going to be over in a second. So we move into EAX, a 1, and then we interrupt the kernel, just like we did here. And like we said before, the very first thing the Linux kernel does is he goes and looks in EAX and says, what is it that you want me to do? He sees, oh, you want me to do magic trick number 1. Oldie but goodie. And what's that? That's sysexit. He doesn't need a whole lot of extra stuff to just quit the program. So he doesn't need any more information. He's just going to close the current process. Take it off the CPU, kill the process, whatever, unload the stuff from memory.
Do you have to move things backwards? It goes E or DCBA and then pulls the kernel. Does it really matter?
Oh, you could have written these 4 lines in any order you wanted.
That's what I thought.
Yeah, you just had to make sure you put the right stuff in the right place. All right. So you're kind of seeing the pattern there. So we're writing something specifically for the Linux operating system. So the idea would be that when you ask the operating system to do stuff for you, it's mostly about staging some information in certain places, then handing the keys to the operating system and telling them to do its thing. And then the operating system comes back and says, okay, look, I did it. And then you go and you stage some more stuff. Go back to the operating system, let him do its thing. This operating system is really important. What did we do before we had those? Not a lot. How many of you have heard of like UNIVAC or EDVAC? There we go. This was a computer. And that's not even the largest. Let's see, largest old computer. Is that EDVAC? Here's an old computer. So these banks of vacuum tubes. So these kind of guys. You'll see it's almost like little light bulbs. All right, so before we had an operating system, or before we had an operating system really did anything, but really almost before we had an operating system, what we're looking at here is a picture of kind of microarchitecture, right? The RAM is inside. Like this, what I have sitting in front of me right here has all this stuff and more sitting inside of it, right? And that's all because of the invention of the transistor, right? What's a transistor?
It's like a gate.
Okay, so look at a picture of one of these things. I'm going to leave that guy up. All right, so this is what our modern day transistors look like. But at the end of the day, we can kind of think of it as being a switch. On or off. 0 or 1. All right, now, if we were building a little prototype of something, we might get a transistor like this. All right, and you get a breadboard. So you kind of take that, you stick the 3 pins in there, and then you hook up your cables, and then it could act as a switch either on or off, whether electricity gets through or doesn't get through. So that determines whether the next thing in line gets power, whether that transistor is letting stuff through or not letting stuff through, right? Now, how many of these transistors are inside of this computer right here? Okay. So if we round down and we'll just say a lot, okay? There's a lot of them. So this is kind of a human visible transistor that you can go and buy. But when we deal with microarchitectures, we've made those guys way smaller than that. We can have a lot of transistors in a very small place. And that's really what happens. Every single year that a new processor comes out, we get more, we are able to squeeze more and more of those transistors into the same space, right? So even though the chip is the same size, it's got more stuff in it. It gives off more heat. And then we figure out, like, oh, well, how can we make it use less power? Well, you move around some magic tricks. You make them require a couple less logic gates and things like that, and all of a sudden you're having to use less power to make it work. Whatever. But we've really made things way smaller. In fact, we're starting to get to the point now where we can't make stuff much more miniature. That's why we're starting to create multiple cores and things like that, because we can only get so many transistors into the same space. But before we had transistors, our computers looked like this. If you wanted something to be on or something to be off, you turned the little light bulb. Turned a vacuum tube on. So you would actually have a little warm-up routine before you use your computer. You got to stretch it out, Then you go use your computer and don't pull a muscle. Okay. So computers really have changed, right? We all knew that. They've really changed. So we're kind of looking at extremes here. So this operating system here is doing a lot of work for us. And I think what's happened to us, and this really goes back to almost the argument we were talking about earlier with Java. If you learn Java as your first programming language, you can accomplish a lot of stuff with Java. Java's a great language. I like Java. But you're kind of being, some important stuff is being hidden from you. And unless you were curious and you went and learned about some of that stuff, you'll never stumble upon it with Java because it hides it from you. Okay, just like I've driven a car for a while, all right? And I know that a long time ago, people used to have to go out in front of their car and crank the engine to get it to start. Similar to how people have to do with lawnmowers. Some of those lawnmowers, you got to pull the little chain thing. Yeah, you used to start your car. Any of you ever had a car where you had to crank it to start it? Aren't you glad? That would really suck in the winter, wouldn't it? Especially since cold engines don't start as easily, right? You might be out there for 45 minutes just cranking. So that's why there were probably less fat people. Everything was an effort. You put effort into everything. You know, heck, now I have auto start. I don't even go outside to turn my car on. I turn it on, and I stay inside all nice and toasty till it warms up. Then I go out. I mean, ultimate laziness, right? Now I'm waiting for the self-driving car, so I don't have to drive it anymore. Just let it schlep me around. Be perfect. Okay. Any of you ever used a horse instead of cars? But we've seen it on TV, right? Yeah. Okay. So then before horses, what did we do before horses?
Walk.
We walked. Who does that? You're telling me you want me to walk? I mean, okay, I live down the street. The grocery store is probably about a 6-minute walk from my house. How often do you think I walk to that grocery store? Well, actually, before my wife and I went on our trip to Israel, we started walking to the grocery store every single day to kind of prepare ourselves for the long walks and stuff we were gonna have to do in Israel. But so there was a reason for it. Well, I mean, for Christians, Israel would be kind of where Jesus did a lot of his stuff. So like we went with our church to Israel. That was a year and a half ago, 2 years ago. We went. Yeah, but yeah, I would say most people don't like make a pilgrimage to Israel. Yeah, it was more just educational thing. Yeah, it's not like part of. Yeah. So it's not like part of the religion. Yeah, they don't. There's not like a list somewhere that says, okay, one of the things you have to do during your lifetime is go to Israel. It's more of just something that people might want to do. But we knew that there was going to be a lot of walking, and it was going to be really hot and things like that. So my wife and I, we made a pact. We decided, we're gonna for the next 2 weeks, we're gonna walk the 6 minutes to that grocery store and really rough it. It was tough. We even invested in one of those little the bags they have by the frozen food stuff in the grocery store to keep it frozen during our long journey. So lazy Americans are so cute sometimes, aren't we? But so the point is that humans, we like things comfortable. Right? We don't want to sit there and do too much with our computer now because we don't have to. That's what we have software for. It does stuff for us. But as computer scientists, we at the very least we want to know what horseback riding was all about, right? We maybe don't want to do it that often, but we want to be able to appreciate how it worked. Okay, so at the very least, we go back. Oh, did I go off that screen? So at a glance, we would say something like this doesn't necessarily look all that friendly, but it certainly is not a wall of zeros and ones. So we prefer this to a wall of zeros and ones. And we're also respecting the fact that that guy right there made this a whole lot shorter for us. Had we not had that operating system in the middle, had we been using something like this, we would have had to give more than those 7 or 8 or 9 instructions to get something to spit out on the screen. Does that make sense? Mm-hmm. All right, so that's a low-level language, what we just looked at here. So as a one-to-one relationship with the CPU. We like the power tools, this one-to-many relationship with the CPU. Okay? So that means we write one line of code, and it turns into a whole bunch of lines of code. So if we're going to do that in Java, let's go back out here to our Java program. Let me just... That's hello world. If I want something to spit out hello world to the screen, I say system.out.println hello world. One line. The rest of the stuff is just normal Java structure. Every Java program looks that way.
So in the low level, you can do logic within the low level. It's just
Well, yeah, because ultimately, when I come in here, so I'm going to store that. When I say javac test.java, I'm running this source code through the Java compiler.
Okay.
And it's going to turn that guy into a class file. Test.class. That is equivalent. That's called Java bytecode. It's assembly. All right. So what ends up happening here when we write our programs, we take a high-level language and we ship it into a compiler. Which then turns it into a low-level language that we ultimately need to run on the CPU. But before it can run on the CPU, we have to take that low-level language and pass it through a tool that can convert it to machine language, which can then run on the CPU. All right, so humans are not going to do the machine language thing. That's not for us. Low-level language, we decided we could if we had to. But we're hesitant. That's a yellow light, right? Here's our go-to move right here. We like those guys. So we want to spend most of our time writing stuff here. Then we'll rely on this complex tool that some smart people wrote that converts a high-level language into a low-level language. So now we have that low-level language. Now at the same time, it's not going to run on the CPU till it's a machine language, till it's a bunch of zeros and ones. So we're going to rely on another tool that some smart people wrote that are going to convert that low-level language into machine language. Now, let's say it was next week's homework assignment. So you got to be in the best behavior, otherwise it might be. Which would you rather write? This guy or this guy? Would you rather write a compiler or an assembler? You'd rather write a compiler?
Well,
Who's doing the harder job? I guess that's really what I'm asking. Maybe you could say a compiler might be more interesting. But assembler is way easier to write than a compiler. What's the job of a compiler?
don't they have they've got a lot of things that they're doing. You've got one line of code in the high level language, and a lot of levels in the low level.
Ultimately, that compiler is going to have to turn this into that low-level language we looked at before for the particular operating system we are on. So it's going to have to convert all that into the appropriate system calls, moving stuff into the correct places of memory. Not only that, it also has to try to do it efficiently. Could I have written a whole bunch of extra stuff in my assembly language program and still have it just print out hello world to the screen? Yeah. So if I have a program that's more complex than this, Might it be that two different compilers, maybe an older compiler and a newer compiler, produce equivalent, functionally equivalent output, but performance-wise, they are different performance-based outputs? Maybe the older compiler doesn't quite create as efficient of a program, of a low-level program, as a newer compiler does. That makes sense? You know, there's some things that in newer compilers, they actually, we might say a shorthand version of this might be that a newer compiler's job is to make a bad programmer look better. So if you write kind of junky but technically correct high-level code, a good compiler will make your low-level equivalent look similar or the same as a good programmer's high-level code would look when it's compiled down to a low-level language. So compilers are difficult, and they keep getting better. Right? So something well, let me ask the question right now. Do you think anybody ever has to program an assembly language today? Why? Under what circumstances?
We're working on kernel, there are some assembly.
Okay.
Some assembly language.
Yeah, it was just because you could. Wouldn't you, if you're working with the kernel, wouldn't you just write it in C?
Yeah, it's mostly written in C.
So why would you write it some assembly sometimes? Just for fun?
To access raw memory.
So the same guy, the whole reason they're out there doing the luge and the bobsled and stuff. It's like, look, I know I'll probably die, but it looks like fun.
Yeah.
The memory you don't access.
Okay, so let me give maybe a better example. So we just kind of talked about that we're at the mercy of how good the compiler is, right? You know, if the compiler turns our high-level language into very efficient low-level language, then most of the time we're fine. So we could mostly rely on that today. Most of our compilers today are good, okay? Now, historically, that might not have been the case. But let's look at a very specific industry today that is a multi-billion-dollar industry, and that's the video game industry. So if you play any video games, especially now, because video games we're not dealing with like old Pac-Man and stuff like that. Video games are, there's more and more explosions and network stuff, and everything's real time and all the stuff. So, and keep in mind that these games now have become so large. How long do you think it takes a gaming company to make one of our big release games these days? Is it a week?
Quite a long time.
So a couple years at least?
Yeah.
Yeah, it might be 2-3 years that they're working on this game. So what do you think graphics cards are going to look like in 3 years? How much faster will graphics cards be in 3 years than they are today? It's a guess, right? I mean, based on history, you can maybe take a somewhat educated guess. But now we're seeing gains that are a little bit less than they used to be. In the early days of computing, things just kept tripling every 15 seconds. We're not in that world anymore. Now, we're looking at percentage gains. You're like, this is 15% faster for a very specific type of task. It's the same for everything else. That's really what you see with every new Intel processor that comes out. This year's Core i7 compared to last year's Core i7 compared to the year before's Core i7, because we're currently on 8th generation Core i7s. Well, a lot of the stuff in the 8th generation Core i7 is the same as the 1st generation Core i7. But there are certain things that each year they've said, oh, we tweaked this, we added this new instruction because we were able to fit more transistors on the same space, so that if you're performing a certain kind of task, this processor is noticeably faster. For many other tasks, it's the same. In fact, it's identical. It is the same. Doesn't have the same performance. It is the same thing. All right. So, but when you're writing one of these video games, you're having to predict what computers will look like in 2 years. Because when these new games come out, you know, now the video games, they have like a tuner in them where you can say, you know, so you can have it on ultra settings, which is like what the game was meant to look like, right? And then you can turn the graphics and stuff all the way down to low for like if you have like a normal person's computer. So the game will actually run. Well, if we think about what ultra settings is going to look like, if you're starting to work on a game today and you want that game to run, to possibly run on ultra settings in 2 years or 3 years when it comes out, you have to make a guess at what computer hardware will be capable of in 2 or 3 years. Because the last thing you want is you want to be that brand new game that just hits the market that somebody with just an average computer can run with everything turned up. You've lost all sorts of street cred. Okay? Even though more people can reasonably play your game, that's not what die-hard gamers want. Die-hard gamers want to say, look, I am like one of 4 people that can run this game on ultra and have a frame rate that's in triple digits or something like that. You know, stupid stuff like that that's relatively meaningless in the big scheme of things. But punchline is, when we talk about gaming, since the gaming industry is pushing the envelope, right? We're constantly trying to make games faster and faster and more. And, you know, there's a point where the game is fast enough because it's, let's call it real time. So then what do? Oh, we got to make it look better. We got all this extra computing resource, so let's just make it better. Higher graphics, more resolution, more explosions, more things happening at the same time, more polygons, whatever, just blah, 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 blah. Now, we're at the mercy of, you know, a question I might ask. So how many of you have a gaming computer at home? Nerds.
Working on building.
Working on, okay, so we'll talk to you then. All right, so why are you going to build a gaming computer?
Well, it's not necessarily a game. I just kind of want to build a computer.
Okay, but you want it to be decent so you can play some games on it or something like that?
I'm not even into gaming that much.
Okay, well, let's pretend like you are.
Sure.
That's an example, okay. So there's some game that just came out that you want to play. And you're going to, you know, you have your budget for your computer, but let's say you had an unlimited budget. So you're going to go out and get the best graphics card, right? So you'll go out and you get the, you know, NVIDIA GTX. There's actually one better than this, but the GTX 1080 Ti. Let's just say that's the card you get, which right now costs a fortune because of all the crypto miners. But, you know, in its heyday, let's say that card had come down to about $600 for that card, maybe $700. It's over $1,000 for a while, but whatever. Expensive card, okay? And let's say that card would give you a frame rate of, on this new game that you wanted to get, of 150 frames a second. Okay, is that pretty good? Seems good? Seems good, okay. How many frames per second can your eye see?
60?
Yeah, so something like 60, right? Okay, so we've had some of this discussion already?
We just briefly.
Okay, so your eye can see about 60. Well, actually, your eye can see about 45 or something like that. Okay, your monitor can put out about 60. Unless you have a gaming monitor, maybe you can put out 120, or maybe you can put out 240. Okay, but the most you can really see is 40. So anything over 40, we're really calling overkill, right? So why did you spend the $600 on that graphics card?
You can put more data per frame.
Frame's a frame.
Yeah.
So the people get these expensive graphics cards not for the average case. There's plenty of, even the brand new game that comes out, there are parts of that game that will run reasonably on lesser hardware. It's when you get into places that have lots of explosions or lots of things happening at the same time, stuff like that, where there's a lot going on the screen, where somebody with a mediocre computer, their frame rate goes from 70 down to 10. Your computer will go from 150 down to 90. You're still fine. The other guy's looking at a flip book because his frame rate's way less than his eye can see. So he's noticing really bad lag, video lag. So the folks that get these expensive graphics cards are getting them not for the average case, but it's for the worst case. So they could play the latest, greatest game with all the graphics turned all the way up so that they're ready for that 1 or 2 second period or the 15-second period when their frame rate would drop way down and it would cause them to lose the game because of that. Make sense? Now, punchline of the whole discussion comes back to this idea that we want games to be fast. And then we have to think of the nature of that compiler. Because we're dealing with high-level languages, so we're going to think of a high-level language like a power tool. All right, so we go out and we buy a chainsaw. That's a power tool, right? Now, the things that we can do with the chainsaw are going to be constrained by the features of the chainsaw. Correct? There might be components of that chainsaw that can do more than we are allowed to do with it because it's been put into the chainsaw form factor and we're just using the public interfaces of that to make it work. Same thing's true with a high-level language. When we use Java or we use C++ or one of these other languages, we are forced to play by the rules of that language. And sometimes the rules of that language will force us to do something. For example, in Java, here, we'll just look at a real example. So let's say I say static int do something. And this guy's going to take a number as a parameter. And I say if num is greater than or equal to 0, return num. So I only actually want to do something if num is a positive number. Okay, or if it's a non-negative number. All right, then I'm going to come up here. I'll do something 15. This gives us an error message because it says we're missing a return statement. The rules of Java say that if we advertise that we're going to return something, we must return something. Now, maybe we know as the programmer that I'm never going to get a value that is less than 0. I just know the nature of the data that my program's processing. And I just happen to know that I'm never going to get a value less than 0. So maybe this is really what we mean. But a language like Java is going to say, oh, okay, well, then we need to throw an else in here, or we'll do it as an else. That way it'll look extra verbose. Maybe we say return -1 or something like that. Now, as the programmer, because we know the nature of the data our program might be processing, we know that this code right here will never get hit. Ever. We know that because we're the ones who write the program. We know the kind of data we're going to be operating on. But Java is not going to let us get away without writing that. It's not going to compile unless we write that. All right, so now this guy will compile. Now, even though we know that this portion of code right here will never be executed in our particular application, it's still going to be represented in the assembly language. It's still going to possibly be add to an inefficiency in that assembly language. So in a situation like that, if this happens to be a part of the game that is really, really critical, has to be super fast, we might choose to go into the assembly language that was produced by our compiler and say, okay, The assembly language is the way it is right now because Java or C++ or whatever required us to do a certain thing. Even though, as the human being, we're smart enough to know that we're never going to have data that's going to break this. Therefore, let's go ahead and clean up some of that assembly code and write it much more streamlined. Break the rules of the high-level language and streamline that low-level, those low-level instructions so that they will accurately operate on the data that we'll actually be dealing with without having to ask all the extra questions, slowing things down. That make sense? So that might be a scenario where we might need to go in and use some assembly code to speed certain aspects of certain things up. Right? We're not talking about real common, but if there's a part of the game that is laggy and needs to be sped up, you might go and look for inefficiencies in the low-level code that's being produced by the compiler because you might have been forced into writing something a certain way in the high-level code because of the language. Make sense? Okay. All right. So we need to play by the rules of the language, which might not produce the most efficient low-level code in the event that we know the nature of our data better than Java does, for example. All right. So back to this picture here, compilers are complex, right? They're hard to write, and they're even harder to write really well. You can probably write a compiler paying no attention to efficiency, just a compiler that converts a high-level language into functionally equivalent low-level code. It's still a hard type of application to write. I mean, that's a difficult program, but that would be far easier than looking at all the different ways you can streamline the low-level code to there's things called unrolling the loop. So if you have a loop that goes through 10 times, maybe the assembly language version of it actually repeats the data of the loop 5 times because it's actually faster than jumping from 2 places back and forth to do it 10 times. Things like that. Now the assembler is a much easier tool because remember, we're going from a low-level language to machine language. These have a one-to-one relationship with each other. All we're doing is we're taking some instruction in this low-level language and we're looking it up for that architecture and saying, this instruction, the move instruction, is associated with instruction 1011 on this particular architecture. So you're just basically converting this low-level language into the equivalent. So you're converting one line of this into the equivalent one line of this. The next line of this into the equivalent next line of this. Make sense? So it's a much easier thing to do. You're just doing the mapping. Right? So this is the guy you'd want to write, even though it might be kind of tedious to write because you're going to have to be looking at the architecture book and saying, okay, well, here's the 4,000 magic tricks that the CPU knows how to do, and here's them listed in binary. Okay, and then you also have to consider the operating system you're writing for. So you're going to spend a lot of your time kind of saying, this is magic trick, this crazy number, and here's the 4 pieces of information we need on this particular operating system to convert it to machine language for that particular architecture. So nothing you're doing is actually going to be all that logically difficult. The algorithm won't be that hard. It's just going to be kind of tedious lookups and things like that to ultimately convert it from something that at least looks somewhat human readable to a wall of zeros and ones. All right, so there's that. There's that. Talked about transistors. Okay, so let's take about a 10-minute break. We'll come back and do our last hour. We're going to talk about memory. We're going to do some C C programming stuff. And then I'll give you a nice impossible assignment to do in C. Right? For you, Edwin.